How is principal component analysis used in data visualization? Have you ever looked at a complex dataset and wondered how to make sense of it? Principal component analysis, often referred to as PCA, is a powerful technique that helps simplify those complicated datasets. It is particularly useful in the fields of data science and analytics trends, especially when it comes to machine learning algorithms in data analysis. PCA works by transforming the original variables into a new set of variables known as principal components. These components are created as linear combinations of the original features. The first principal component captures the most variation in the data, while the second captures the next most, and so forth. This transformation allows you to focus on the most important patterns in the data, summarizing it with fewer dimensions. When it comes to data visualization, PCA shines in high-dimensional datasets, which are datasets with many variables. Humans can easily interpret 2- or 3-dimensional plots, but anything beyond that can be overwhelming. PCA reduces high-dimensional data into 2 or 3 dimensions, making it possible to create scatter plots or other visualizations. This can reveal structures, clusters, or outliers that may be hidden in the original data. For instance, a dataset with dozens of features can be simplified to just 2 principal components, which can then be plotted on a 2-dimensional graph. This often makes patterns and groupings much clearer. A key concept in PCA visualization is explained variance. This metric indicates how much of the original data's variation is captured by each principal component. Typically, the first component explains the most variance, with each subsequent component explaining less. By examining a scree plot or cumulative variance plot, you can determine how many components to retain. This helps balance the need for simplicity with the risk of losing essential information. PCA is not just about creating appealing visuals. In general computing and emerging technology, PCA-driven visualization serves as a practical step in exploratory data analysis. It allows data scientists and analysts to quickly identify whether a dataset has clear patterns, if different groups or clusters exist, and which machine learning approaches may be most effective. For example, if a 2-dimensional PCA plot shows well-separated clusters, a clustering algorithm might be a good fit. If the data appears mixed, more complex models may be necessary. The applications of PCA in visualization are extensive. In image processing, PCA can compress images by retaining only the most significant components, which makes storage and transmission more efficient. In healthcare analytics, PCA helps visualize patient data to identify early signs of disease. In any field dealing with large, complex datasets, PCA visualization is often a first step to understand the data's structure before building models or making decisions. However, PCA does have limitations. The new components can be challenging to interpret since they are combinations of the original variables. Additionally, PCA assumes that the main patterns in the data are linear, which may not always hold true. Despite these challenges, PCA remains a standard tool in data science for making high-dimensional data accessible and actionable through visualization.